So good morning, good afternoon, good evening to all of you. I am calling from Hawaii, where I just moved, and yes, it's 4 a.m. in the morning, and yes, I cannot wait for this talk to be over so that I can go to sleep. So I'm going to talk about on-sky NCP creation through the pyramid wavefront sensor, through the reference update. So my supervisor are Olivier Guyon and Antoine Boucaletti, but I would like to give a special thank to Eric Gendron, who has been very helpful. Now I joined the SCAXO team. So as you know, direct imaging of exoplanets is extremely challenging, and this is for several reasons. The main one is due to speckle subtraction, that the speckle that make the exoplanet signal, and there are a mix of atmospheric residuals and non-common path aberrations. So I guess you all know what it is. They have been introduced quite a lot in the previous talks, and there are several kinds of NCPA: the static, the quasi-static, and the dynamics. And each kind have low and high spatial frequencies. So there are several ways to deal with those non-common path aberration, as they have been introduced in previous talks and will in the future. And this can also be partially solved by changing the gain. However, in extreme adaptive optics, the gains are coupled. So I'm going to introduce a method that is complementary to this. So let's go to the heart of the problem. So Drwho, first of all, stands for, is the algorithm that I'm developing. It stands for direct reinforcement wavefront heuristic optimization. And no, I didn't find the name myself, but I find it pretty cool. So the problematic is what is the pyramid reference, the pyramid wavefront sensor reference? In other words, what gives a flat wavefront? What gives an image without speckles? So what happens during the observation is that we measure the wavefront sensor reference with an internal source before the observations, and but this reference is constantly evolving and it's different on skies than with the internal source. So it's constantly changing, and we need it is essential to have a continuous way to measure the wavefront sensor reference, and which is different from the ideal wavefronts that we of course try to get as close as we can. So this is true for every kind of wavefront sensor, but a special bonus for the pyramid wavefront sensor for its very annoying nonlinearities, and those nonlinearities are sadly intrinsically linked with the non-common path aberration problem. So let me now introduce what is actually the Drwho algorithm. So the idea is as follows. So while the adaptive optics loop is running, we have a live update of the pyramid wavefront sensor. This is done through first. So we take a 30-second time scale, and the algorithm identifies the base 10% Drwho ratio. It could be the Drwho ratio, it could be the contrast, the sharpness, the minimum intensity, basically any kind of reward that you want. And then you take the corresponding wavefront sensor measurements that correspond to those 10% best images that you have on the short exposure PSFs. So then that you have your wavefront sensor measurements, you average them, corresponding to the 10%, and you weight them on the Drwho ratio value or whatever your reward is, so that basically you give better weight to the better images that you have. And so that gives you an average one. So the resulting wavefront sensor frame replaces the wavefront sensor reference with an integrator filter, of course, to avoid any kind of divergence issue. So as the algorithm proceeds, so every 30 seconds, it is continuously rewarded for high quality PSF. So we did some tests on Sky, on SCAXO with the Vampire instruments. So we have, as you can see here on the left-hand side, you have a PSF with a pretty strong coma. And for over a 21-minute period, you can see that slowly, as the algorithm proceeds, the PSF gets better and better with a sharper PSF. And regarding I did actually also some simulations with the Compass simulator. So without NCPA, I have a 30% Drwho ratio, and I add a lot of NCPA that drops the Drwho ratio at 81%. Here on the left-hand side, that's the red dot that you can see. And then as the algorithm proceeds, here it's after a few iterations of the Drwho algorithms. So as the algorithm proceeds, you have you update the reference of the wavefront sensor, and then you reach a level of a much better Stride ratio at 80 to 88%. So this is still not 93%, but this is still a very huge improvement compared to the case without any NCPA. So this is actually also by just doing some basic lucky imaging on based on just considering the reward or the whole PSF just as the Stride ratio. So now let's try to maybe have a look at how we can be maybe even smarter on how we look at those images. So we want to take advantage of the difference in the spatial frequency of the PSF. So the way we do that is we look at the PSF short exposure, and we know that the inner zone of the PSF, let's call it the donuts, it's a place of is an area of low frequency zone, and the outer part of the PSF it's an area of higher frequency zone. So we can basically separate the PSF into spatial frequencies with the closer you get from the center, the lower your frequencies and the outer you get, and the higher spatial frequencies you have. So we can see here the right hand side is quite a good example of those modes. You can see that on the outer edge of the PSF you do have much higher spatial frequencies. So as I said, the inner donut has a lower spatial frequency than the outer donut, so we can actually select part of the image corresponding to the spatial frequencies that we want on the wavefront sensor image. So here we can have two loops in this example, two loops of that Drwho algorithm for each donut, the inner one and the outer one, sorry. And so we can basically separate lower and higher spatial frequency and correct them independently. So we have two loops of Drwho algorithms that run in parallel, and then finally we sum the two references given by the two zones, and we find the wavefront sensor image reference. Sorry. So how far can we do that? So I gave you an example with two donuts. So can we go even further by making even more donuts? And this is how I got quite excited during the lockdown. And basically we can have as many donuts as we want to separate in spatial frequencies within, of course, some limits of linearities. So basically, this is a way to have an accurate quantification of NCPAs and project NCPAs on basically your favorite model basis. And for me, my favorite one is by far the Drwho model basis, and the paper is in progress by Drwho et al. 20-something. So now, how can you go even further? How can we think things differently? And we can think through Fourier spatial filtering of the wavefront sensor image via zones in the PSF. So I'm going to explain. It's going to get a bit messy, but no worries. I'm going to try to go step by step. So first of all, we look at the short exposure PSF just like previously, but now instead of having donuts, we divide the PSF into kind of square-ish zones. Well, square zones. I'm not going to talk about how the center works because the center is kind of a different part, but let's just consider things simply for now with just square zones. So for each of those zones, we get the intensities. So of course, except for the center, we will want to minimize the intensity in those zones to increase the contrast of our image and to better detect planets, of course. So we have basically as many intensities as we have zones. And out of those intensities, if we sum them up, we reach the total intensity of the PSF. And then, just like previously, we take the 10% best values and the corresponding wavefront sensor filtered image. So how we do that, we look at the wavefront sensor images independently. We go through a Fourier filtering per zone. So again, that gives us as many filtered images as there are zones. And out of those filtered images, we look at the ones that are corresponding to the 10% best values, and And we go back to the wavefront sensor space, and that gives us basically the resulting slopes. I don't want to say slope because it doesn't make sense to talk about slope for a pyramid, but whatever, let's say slopes. That gives us basically just the 10% best images, and that we can sum up to have the final reference. And if we sum actually also all those filtered images, we end up having the final slopes that Compass gives. So now I think I'm reaching nearly my time. So I will first give like a first summary actually of my presentation. So as you can see here on the left, we start from the NCPA, and this is where the Drwho algorithm comes in and try to better understand what are those NCPAs and correct them with the pyramid wavefront sensor reference. However, this tricky pyramid wavefront sensor is non-linear, so that gives us a kind of wrong understanding of the NCPA, yet still good enough to correct some of them. However, still it's not 100% good. So it still gives a partially wrong comment to the deformable mirror, and therefore a wrong correction to the of the NCPA. And then we go back and forth as the algorithm proceeds, and as the observation keeps going, we reach a better understanding of those NCPAs and a better correction of those NCPAs. So a few comments on this algorithm, this method. So this parallelization of the optimization is actually quite powerful, and especially in increasing the speed of the algorithm, because if you take only the stress ratio, it can take quite some time. However, by parallelizing, that makes it even faster and even easier for the computing power and time. So you can have each area, either a donut or squares, that runs optimally in parallel. So you have one Drwho algorithm that runs for each area, and each working on separate modes or special frequencies. So this algorithm is also pretty flexible in the choice of optimization, either in terms of the kind of zones that you want to use and their size as well. If you want to have different kind of donuts, I tried at some point with 20 donuts, and that ended up being completely messy, but you can do essentially whatever you want. And same for the size of the zones. You can have a zone that is the size of 1 lambda over d, and that's would actually quite good in understanding as well the speckles and what is their special frequency and how to better correct them. Also, it's pretty flexible in the frequency filtering that you want to use, whether you want to use the Drwho model basis or you want to go through Fourier. And then you can you are free as well to use the quantity to optimize, whether you want to optimize a local contrast, the stress ratio, you want to minimize the intensity, or basically whatever you want. Also, the Drwho algorithm, it's flexible on the time setting. You can decide to optimize it on 30 seconds or in 10 seconds if you really want to go fast, or even much longer if you really don't really care about the dynamic NCPAs, but who doesn't care about the dynamic NCPAs? Anyway, so same for the lucky imaging setting. You can actually decide to take only the best 1%, and that will make you converge even faster. And this is actually something that I'm exploring at the moment. Like, what are the algorithm setups so that optimizes the speed of convergence of the contrast. And then you can use it, of course, with the Shackman, but ideally was, well, actually not really ideally, but any kind of wavefront sensor that you want. And I'm actually looking at, especially for the pyramid wavefront sensor, especially because of the nonlinearities and its interesting aspects. So following the previous session as well, there are a lot of possible extensions to this algorithm. And one of the aspects of my PhD, by the way, I'm a first year PhD student, so please don't be too mean in your questions. There are a lot of ways on which we can have an empirical approach to better understand what are the nonlinear relationship between the modes and the PSF and well, basically the wavefront sensor images as well. So thank you very well. Next step is, of course, to install it on the Skexo team, on the Skexo bench, and on Sky. And thank you very much for your attention.
Thank you very much, Nour. Thank you. So there are a couple of questions, and they are all related to the basis. So if you can say a little bit more on that, it would be nice. The Drwho basis.
So I don't know who asked the question, but I think the
best person here and Olivia asked the question.
I'm not sure I can really explain what is the Drwho model basis, and I'm not sure I'm supposed to explain what is the Drwho model basis, because it's the paper is far from being ready yet.
So maybe we can ask Eric to answer to the question in the site.
Hello, everybody.
Eric can rapidly answer to the question. Yeah.
Hello, everyone.
Hello, Drwho.
So this basis has something special, which is that each of its mode has a particular spatial frequency, but contrarily to Fourier basis, which is only one single frequency, the frequency contents of each mode is a ring. So the modulus of the spatial frequency is constant. So the mode really look like Karhunen-Love mode, and each of them, the Fourier transform or the PSF associated to each of them is a ring and nothing else. And that's what makes it a little bit special and useful for when you're dealing with spatial frequencies. That's it.
And that's why it's my favorite one.
Thank you. So there are other questions. One from Stephen Boss. So can you show more simulation lab on Sky results of Drwho with these additional zones? So do you have some results or?
So what I can show, wait, where is it this one? Yes. So actually, I cannot show any. I haven't actually started to work. Am I muted?
Sorry?
No, sorry. I thought I was muted for a second.
No.
No, actually, I haven't. I haven't started to work on the bench yet. And this is actually just why I just here right here. Actually, I'm to join the Skexo team. What I can show you is a compass simulation on what I was doing on. Remember the 2 donuts thing? So here is just a simulation over a few iterations, and on 10 seconds of loop iteration, I have that second is actually really short, but on my computer that runs at 8 kilohertz, it took me like a good half an hour. So I have a stress ratio improvement of 4%. So this is just for the case of the 2 dollars, and we see that clearly the intensity. Sorry, the yellow is the intensity, the blue is the shell evolution, and we don't really see very well, but the shell quite evolves. But yeah, new results and real data are coming up very soon. Stay tuned.
So thank you very much. So I suggest we can continue the discussion on Slack, and we can move on for the next speaker. Thank you very much, Nour.
Thanks to you.